morning, all of you. And last time we have stopped until I think, as I remember, it's until we did 8th question. Then we will start. I mean, we can continue from the 9th one. And let me share the screen first. Okay, can anyone confirm it where we stopped last time? Can anyone tell me? 7th question or 8th question we did last time. BS 53. Guys, can anyone? Okay, one person. Can anyone tell which question we have stopped? Okay, then let me talk from 8th question. As I remember, so we show that the perpendicular distance between adjacent planes of a set HK in a simple cubic lattice of a lattice constant A is, you have to prove the perpendicular distance. If we are talking about the perpendicular distance between adjacent planes, you have to, it's directly, you can think about the orthogonal axes. As you all know, I mean, if we want to look at the answer, it's totally in your theory, I mean, in your notes PDF, you can check it. We can briefly explain. If it is as mentioned in the question, if it is a perpendicular distance between adjacent plane, then it's directly, you can think about orthogonal. If you want to think about the orthogonal plexes are, it's perpendicular to each other. So in this case, DHKL is the distance, right? You have to think about the distance between two parallel crystals. So you have to find you have to find the equation for a D value. So in this case, you can get it vector based equations for the D based on the, alpha, beta, gamma in this axis. So you can easily get the relationship between alpha, beta, gamma for the orthogonal axes. Using that, you can substitute the values, previous value. We got already 3 values, equational values. So you have to substitute those equations values in this equation. And at the same time, as you all know, the HKL are Miller indices, right? So using the common factor and intercept values, you can get the simplified equation for the HKL. So after substituting those values as well in the equation of the D value, you can get the equation based on the HKL and ABC as a squared, in the squared form of equation. Using a common vector factor, so A, B, C both are equal. So you can consider it as A only, so that you can get the interplanar spacing distance of a cubic lattice is it's equal A over square root H squared plus K squared plus L squared. You can easily get it at the same time. This is proof in senior, theory, your notes. You can check it as well. Then we will move to the next question. Then 9th question. For a body-centered lattice built up for a spherical atoms of radius r in nanometer, calculate the number of atoms per centimeter cube on the plan. There are certain plans. So do the same for the face-centered and simple cubic lattice. Okay, let me tell about something. Number of atoms per centimeter square means we can easily tell that is planar density. Planar density. So we are going to discuss about the planar density for the 9th question. So number of atoms per the centimeter squared, it's equal planar density. So PD it's equal number of atoms in the particular plan divided by area of the plan. In this question, they are asking for the first part as the first part. We have to do this, PD calculation for the body center cubic for a certain plane values. So first they have given 100. As you all know, if it is 100, you have to think about only x-axis as a one value. So you can easily get it. So you can get the value for x-axis only. Both the other intercept lengths are infinity. So you can get it. Okay, let me show you. You can get it like this way, right? So in this case, see, number of atoms in the plan of the given plan 100. So see 1/4 in 4 corners. So you can get it 1. At the same time, number of area of the plane is it's equal to a square because it's very easy to understand. It's just a square. So you have to substitute both the number of atoms value and the number of plane in the PD equation. But the problem is you can't give the answer in simple A, right? Because they have given you the only value as R as only value. So that you have to convert the simple A. See the corner, right? So you have to convert the simple A value into capital R because they have only given capital R. So you have to give the answer in capital R based, right? For this case, as I see in this question, you can get it. So in this diagram, you can get it, right? So if this using a Pythagoras theorem, you can get this 4R. See, there are middle. If this, sorry, if this because if this atom's radius is simple r, this length should be 4r. So this 4r should be equal to 3 square, square root 3a. You can get this square root 3a value using the Pythagoras theorem. It's all a very simple mathematics. So you have to convert this simple a value into capital R, and you after getting that simplified value of simple a, you can substitute and you can get the number of atoms per centimeter squared in the R value. You can easily get it for this plan, certain plan. Okay, then we will move to the next example. They have asked me for another part, right? So next plan, they have given the coordinates of other plan 110. In this case, x and y has values, right? So you can get it. So you can get it in both direction, and only z has infinitive. So your plan should be in this way. So again, as this body centered, you have a center atom, and there are 1/4 in 4 corners. So you will easily get the idea of the plan and atoms. So that number of atoms is middle one and corner 1. So totally 2. And area of the plan also you can calculate using Pythagoras theorem. So you can easily substitute those values in PD equation. So we can move to the next next plan coordinates. Okay, so you can substitute those values and you can easily get the PD value for this question as well. See, this plan coordinates like 1 1 1. So you can easily get it like it should be a triangular shaped plan. So that in this case, so it should be, you can think about if this is this triangular planar should be this triangular should be an equilateral triangle. So this these atoms, this portion, I think you can easily observe as I guess. Let me check again. Sorry, I couldn't zoom it as I guess. Okay, so this portion, this angle should be 60. So using that 60, this should be 1 over 6 and 3 edges has the atoms. So this number of atoms should be half. And the same time using the Pythagoras theorem at the same time, using the area of triangular, you can get the area of the plane. And using that easily you can get the PD value for this 111 milliindices for the body centered, right? Then we will move to we have to do this for this again face centered cubic. See, in this case, so face centered means only we have atoms in the face base, not body centered. So in this case, for first coordinates 1, 0, 0. So think about it, and this should be the plan, exact plan what we want to do. And see body, if it is a face center, there is a center atom and 4 edges has the 1 by 4th. So you can get it like atom number of atoms in this particular plan is 2. Then at the same time this area should be a squared. Then you have to get it in capital R. So you can easily get the PD value for this 100. Then we will move to the 110. Okay, let me explain about the 110. See, again, you know about the plan. Already we did for the other example. In this case, there is no, see, only H atoms are influencing in this calculation. Because in this particular plan, see, in this particular plan, we are talking about the face center. So those whole face center atoms are not influencing in this middle particular 110 axis. So that purpose, so that you don't want to think about the face centered atoms. So you will get this way. So you have to calculate the number of atoms in the particular plan, and 1 by 4th are in 4 edges and half atoms are in the 2 sides. So you will get the number of atoms as 2. Then again you have to get the area of the plan. Again you can get it like, see, if it is this should be simple a, and you can get this value as square root 2a using Pythagoras. So you can easily get it, and you get the PD value of 110 for FCC. So then we will move to the next example for this face centered. So that should be 111, right? So again the same thing happening here as well. See, this is a triangular plane, so you can easily get, as it is a face centered. See, in all those 3 sides of triangle has half of the atom. So you have to get the calculated, you have to get the atoms of number of atoms in the particular plan. So it should be 2. So you can get the area as well, like previous examples. So again, it's quite easy to do you all, as I guess. So we can do this question for the as well as simple cubic, right? So can anyone do this question for me? Only 100. Do you have any idea? Okay. Okay, let me ask one person then. PS004. Are you all trying this question?
Yes, Miss. I try.
Okay. If you try, you can tell me the answer and we can check it. Just we can check, we can try it. Okay, you can try, guys. Then we can discuss and we can think about you all get the idea or not? You have to do this for only simple cubic for this particular plan coordinates 1, 0, 0. Can anyone tell the answer for the PD value of this 100 for simple cubic? Okay, shall I ask someone? We will go to a person. BS80. Oh, BS80. BS23. Okay, I think, okay, guys, tell me then, can you understand the question of this procedure? Should I explain it some deeply? I'm not sure what you're doing actually. Okay, then we will move to the explanation. Okay, I'll ask one more person. BS53.
Yes, miss.
Have you tried this question?
Try.
Should I explain? Yeah, okay. Should I explain this question or can you understand this?
Can you explain again, miss?
Yeah, okay, then let me explain again. Wait a minute. See, for this simple cubic, you have to think about 100, right? 100 means it should be, you can get the sketch, axis sketch of this particular planet. As you all know, this resembles the plan coordinates, right? So using this plan coordinates 100, you can get the idea about the plan sketch like this. So after getting this detailed view of this particular plan, you can think about the how many atoms in this particular plan. So that, as you all know, if it is a simple cubic, there are only 4 atoms in the edges. So using that idea, you have to get the number of atoms in this particular plan. So at the same time, you can easily get the area as it is a squared. So you have to convert that value in R, because see, this atom's radius should be R. So A should be, A it's equal to 2R. They have mentioned here, see. And you have to substitute the A squared value in capital R. So easily you can get the PD value. You can substitute the number of atoms and area in the PD equation. And easily you can get the PD finalized answer. So then we will try another example, another part. So in this case, see, for the simple cubic, that planar coordinates indicates 110. So it should be like this. Again, it has this plan also having 4 atoms in the edges. So in this case, again, you have to think now the number of atoms should be 1, but the area of the plan it's different in here, because see, in this case this length should be A, but the width should be not it's equal to A, because this should be square root 2A. You have to get it using the basic idea. So using those values, you have to get the area of the plan as in capital R value. So you have to substitute both values in PD equation. As like that, you have to do this same method for another example as well. Those coordinates are 111. So this plan should be, as the previous example, this should be triangular. So you all know those 3 atoms are in the edges only, because it's simple cubic. So you can get the idea about the number of atoms in the plan. So it should be half, because it's a equilateral triangular. So using that basic concept, you can get the PD value for this coordinate 111 for simple cubic. I guess it's very easy calculation. Then you can get the idea after getting the answers, as I guess. Okay, then we will move to the next question. What is the spacing between the 100 plans of the simple cubic crystal if the spacing between 111 plans of crystal is 1.80 angstrom? So they have given you one particular D value for the particular plan, and they are asking another D value for the another plan, but the same crystal. First, see, of a simple cubic crystal. So it's a simple a particular one crystal, but they are asking for these different, I mean, they are giving 2 different Miller indices set of planar coordinates, and they are asking for the different D values. So as you all know, you all have proven, previously we have proven an equation, right? Wait, let me show you. So in this case, interplanar spacing D, it's equal is for a cubic cell. You can easily get the idea about this D value using this equation. See, this D is equal, A is it's a lattice constant, and HKL, those are called Miller indices, right? So as you all know, that should be as a 3 values in a particular bracket. So in this question, they have given 2 different sets of HKL values, and you have to get the D values at the same time. This simple A value should be equal for both cases, because that should be, because that should be same, because that these 2 Miller indices are given for a particular same crystal. So you can easily get the D value for that another case. So let me show you how to do the calculations for this question. Okay, see, they have already given the distance, planar distance of a particular plan 111 is 1.8 angstrom. So you can, after substituting these values in the, you know these Miller indices for this plan particular question, it's HKLI equal to 1. So you can substitute those values, and as they given 1.8 is the interplanar space simple day, so you can substitute that as well, so that you can get the value of the crystal constant or lattice constant simply using the previous values they given. So using that simple a value, again, they are asking the d value of the 100. So in this case, you already found the simple a value. At the same time, HKLR, see, these three are the HKL values, right? So you have to substitute those three and you can easily get the interplanar distance for 100 using the previous calculations, because this is for the same crystal lattice. That's why you can easily compare the values and you can easily get the interplanar distance. So the next question also is very similar to this question. Okay, we will move to that question quickly. Okay, see, 11th question. Show that for a simple cubic lattice, D100, D110, D111, it's equal square root 6, square root 3, square root 2. You have to do the simple calculation using the interplanar spacing equation and you can get the comparison with those three planar coordinates. So we will do that simple calculation and we can get the comparison. So see, the same thing you have to do. You have to get the basic equation here. So let me see. You all know this equation. You have to substitute for every condition. So you all know the Miller indices in this equation, so you can substitute. At the same time, as if it is a same crystal, so you can easily substitute simple A is equal like same way. So you can get the answers in simple A. So you can get the D values in simple A like this way. So after comparing in simple A, you can easily simplify. So in this answer, they have mentioned square root A. That is not square root A, guys. That should be wait, let me clear it. So see, in this question, this is wrong. It's a by mistake. It should be 2. So after simplifying by A, you can easily get the comparison like square root 6, square root 3, and square root 2. So you can easily tell the interplanar distance having this kind of comparison, this amount of compare. Okay, so this is the very easiest question based on the interplanar distance calculations. So it's very easy. So please check before your assessment and exams, right? Okay, then let me go to the next part of the tutorial. Okay. The next question should be, thinking of atoms as a hard sphere of radius r, calculate the packing fraction of a simple cubic, body-centered cubic and face-centered cubic unit cells in a closed packed structure. As you all know, it's also this question also based on the theoretical thing. You all know what is packing fraction. So packing fraction is equal to number of atoms in a unit cells, number of atoms in, APF it's equal to volume of atoms in unit cell and volume of the unit cell. So it should be how these atoms are occupying the volume of that particular unit cell. You have to compare both volumes and you have to get how those atoms are packed in those particular unit volume, unit cell of that, volume of that unit cell. So you have to compare those two volumes, right? For that purpose, we will only check one question here for the FCC. So they are asking here, C for the FCC and BCC at the same time SC. Simple cubic, body centered and face centered, right? So we will see only one thing. It's very easy. So in this case, this detailed equation is in your theory. You can check in your notes. So you have to substitute the, again, you all know how to get that 4R value in simple A and 4R R and A relationship. So you have to get the number of atoms. See, in this case, you have to get the idea of the number of atoms and volume of the all those atoms. So first of all, you have to get how many atoms in this particular unit cell, and you have to get one atom's volume, and you have to get the total volume of the atoms, and you have to get the, see, this that A cube should be volume of the unit cell in this equation. In this case, see, number of unit cell is, so this should be, this upper portion should be volume of total atoms in that unit cell. So you have to get it, and total, the upper lower part is volume of the unit cell. So you have to substitute the values, and you can get the APF value using a simple calculation. See, you have to get the, so this should be the volume of one particular atom. Then this is number of atoms in that unit cell, and this should be volume of the unit cell. So after simplifying, you can get this APF value. This is kind of 74%. These atoms are occupying the unit cell. So this is the basic thing. You can easily do for rest of the other parts as well. So we will move to the 13th question. So write down the primitive direct lattice vector of SC, BCC, FCC lattice systems and indicate the primitive unit cells in such systems. I think all these questions are very simple and all are related to your notes because you all studied all these stuff. So don't think much, you can easily do. So in this case, for the SC, simple cubic, you can easily get the primitive direct lattice vectors A1, A2, A3 based on the X, Y, Z axis values. Using the intercept length values, you can get the primitive direct lattice vector. But the thing is, see, write down the primitive direct lattice vector for an FCC direct to indicate the primitive unit cell. So they have written for the, only they are asking the direct lattice vector for all three. So here we wrote for the SC, simple cubic. And again, you have to write for the BCC. As you all know, you have to mark it those unit cell in the axis sketch. And again, you have to give these three BCC primitive direct lattice vectors for BCC, and you have to mark it down the primitive unit cell. And the third one is FCC, right? So in the FCC case also, you have to write down those three primitive unit vector, primitive direct lattice vector, and you have to mark it down the primitive unit cell in the sketch. So we will go to 14th question. It's kind of a 13th question is direct question, and you can get the idea from you. Your madam has given you the lattice vectors in theory, and you have even the diagrams as well of the system. So you can easily understand the diagrams, and you can easily get the idea of the lattice vector from your theory. So 14th question, show that reciprocal lattice of FCC lattice a direct lattice of BCC. So you have to think, we all talk about the lattice, direct lattice in the 13th question, right? So here they are asking about the reciprocal lattice. This question is based on there is a subunit in your theory, reciprocal lattice, right? So you have to get into that part to discuss this one. And that should be, as I guess, that should be from lecture note 5. So we will discuss about that, okay? So we have to think about the direct lattice and reciprocal lattice vector. So here, so we all know from our theory, BCC direct lattice vector, A1, A2, A3. At the same time, you know the FCC primitive vector, right? So you have to get the primitive lattice, see these two vector values all already given, right? For that, but you want to think about the reciprocal lattice of the FCC. For this purpose, you already given in the reciprocal equation. This is called reciprocal lattice equation. So these A2, A3, those are called as primitive translational vectors. Using those translational vectors, see these three, these are called primitive translational vector. So using the primitive vector or direct lattice vector, you have to get the reciprocal lattice of FCC. So you have to see, you already have these values here. For A1, A2, A3. To get the reciprocal lattice value, you have to substitute that A1, A2, A3 value in this equation. So that you have to, these reciprocal lattice of FCC here, we can call them B1, B2, B3. See, you can easily get the simplified answer in terms of 4 pi over A into half Y plus Z minus X. Okay, while looking at this simplified answer, you can get it. See, it's really similar to, this is right. You can compare this value. So reciprocal lattice of FCC is getting, it's equal to BCC direct lattice in terms of 4 pi over A. You see, everything is like that. So reciprocal lattice of FCC is in terms value of direct lattice of BCC. That's what they are asking us to prove. So you easily tell that these FCC primitive vectors are direct lattice BCC value in terms of 4 pi A. This 4 pi A is called like lattice constant. So this is what they are asking you to prove. So it is equal to, the FCC primitive vectors are equal to BCC direct lattice in terms of lattice constant. So see, in 14 question, show that reciprocal lattice of FCC lattice is direct lattice of BCC lattice. So using these equations, you can easily show that what is the connection between FCC primitive and BCC direct lattice. So we can move to the 15th unit cell, has a dimensions Okay, 15 dimensions. A, this second should be B, C, and they have given alpha beta is 90 degree and gamma should be 120. Determine the followings, and this A star, B star, C star for the reciprocal lattice. Okay, can you identify what are those A, B, C values in part A? Those are called primitive vectors, right? In the reciprocal lattice equation. So primitive vectors or primitive translational vectors, we can call like that. For that, for that requirement, you have to use this reciprocal lattice equation. So they all given the equation, I mean values for A, B, C for the primitive vector calculation. So you have to calculate, I mean you have to substitute the A, B, C values in the equation, and you can get the answer in terms of pi. So after substituting value for pi, you can get the primitive vector A, B, C values, and you can easily get those in simple calculations. So that's the first part. And the volume of the real and reciprocal unit cell. So you have to get the volume of real and reciprocal unit cell. See, as they given A, B, C, those are actual lengths, right? Actual intercept lengths. So using those lengths, you can easily get the volume of unit cells, right? Okay, let me clear this. So using that actual intercept lengths, you can easily substitute those A, B, C, and you can get the volume of the unit cell. That is totally fine. We can easily get it. But the next thing should be, you have to find volume of the reciprocal lattice. For the reciprocal lattice volume, you have to get the A star, B star, C star. So you want those three. For that purpose, you have to get those values in terms of pi. But the problem is they have given the values in actual angle, right? In degree, they have given the values of alpha, beta, and gamma. So you have to convert those in red values in pi. So you have to you have to substitute those angle value in red values. So see pi by 2, because what is the A value? See, let me. Four, 6, 8, right? So using that, you have to calculate the A, B, C values. So using that not finalized numerical value, you already had a value in pi, right? So using that pi values, you can easily substitute pi by 2, pi by 3, and pi by 4 in this volume of reciprocal lattice equation, and you can easily get the volume of reciprocal lattice. These are the questions. You can easily get it. Madam will share the answers with you later on. And let me, okay, one person asked one question. Okay, I'll clarify that part because there is a small theoretical mistake in this question due to the answers. Let me explain you. Okay, in this comparison, so see guys, number of atoms in a primitive unit cell is 1, it's totally fine. But the second point is atoms in the primitive unit cell is equal to the number of atoms in larger cell. Is that correct? Actually, I'm really sorry. I also didn't focus on this point last time very clearly. So I also explained, I also misunderstood that. So it can't be equal. See, it can't be, definitely can't be equal. You have to omit this point, okay? You don't want to think about this point. It can't be equal. That is the thing I have to inform you. And I hope you all understood these things. And if after getting the answer script, you can try these questions by your own. You can have a clear idea on these questions and try it again and again before the exams and practice yourselves in this part. Anyhow, let me take your attendance.